Hello everyone, I'm Dr. Manju Gupta, Department of Chemistry, St. Aloysius College, Jabalpur. Today I'm going to explain another spectroscopy, that is infrared spectroscopy, and its basic principle. In my previous lectures, we were discussing about UV visible spectroscopy. Information obtained by UV visible spectroscopy was related with the presence of carbonyl group in the molecule, presence of carbon-carbon double bond or carbon-carbon triple bond in the molecule, or presence of conjugation in the molecule. Suppose if we have a carbonyl compound and if we want to have an approximate structure of the molecule, its nature, whether it is aliphatic and aromatic, this information do not provided by the UV visible spectroscopy. UV visible spectroscopy only provide information about the presence of carbonyl group, that is C double bond O. It is silent about this carbonyl is acidic, aldehydic, ketonic, or any other group. So it is only provide information about a broad range, that is carbonyl group. Similarly, this UV spectroscopy is silent about the presence of OH bond in the molecule, hydrogen bonding present in the molecule, or it do not provide any information about the polarity of molecule. IR spectrum provide information about the functional groups present in the molecule. The whole IR region is divided into 3 parts. The whole IR region is from 0.8 to 200 micron. 0.8 to 200 micron. This whole region is divided into 3 classes: 0.8 to 2.5 micron. This is near IR. From 2.5 micron to 15 micron wavelength IR. This is known as working IR or main IR region. From 15 micron to 200 micron, it is far IR region. As in UV visible spectroscopy, wavelength unit is used or recorded. In IR spectroscopy, wave number unit is used. If we want to convert wavelength values in the wave number, we can convert wavelength by using this equation into the wave number. Suppose wavelength is 2.5 microns. So first we have to convert it into centimeter inverse. 2.5 into 10 to the power minus 4 centimeter inverse, minus 4 centimeter. And when we put this value in the equation, then it is 4000 centimeter inverse. Energy required for this range, the main IR range, is from 4000 centimeter inverse to 400 centimeter inverse. If we want to calculate its energy, we can use this equation. E is equal to NaHc nu bar, where N is the Avogadro number, H is the Planck's constant, and C is the velocity of light. For 4000 centimeter inverse, the value of energy is 50 kilojoule per mole. For 400 centimeter inverse, the energy is 5 kilojoule per mole. That means the energy range of IR spectrum is from 4000 centimeter inverse to 400 centimeter inverse. The interaction of IR radiation with the sample is similar as in the UV spectroscopy. When we irradiate any sample by IR radiation, some of amount of light is absorbed by the sample and some of the amount is transmitted by the sample, and any one fraction can be recorded by the detector. In UV spectrum, generally absorption spectrum is plotted. Absorbance is plotted against the wavelength. In place of wavelength, in IR spectrum, wave number unit is used. Wave number can be plotted against the absorbance or against the percentage transmittance. If we plot absorbance against the wave number, we obtain this type of spectrum. This spectrum is absorbance spectrum. Since absorbance is inversely related with the transmittance, when we convert absorbance into percentage transmittance, this spectrum will be inverted. Generally, in IR spectrum, percentage transmittance is plotted against the wave number value. The principle of IR spectroscopy is based on the same as of UV spectroscopy. Same way, in a molecule, three types of energy levels are possible: electronic, vibrational, and rotational. And in a single electronic level, different vibrational and rotational energy levels are present. When we apply IR radiations has less energy than the UV visible radiation. Electronic transitions are not possible, but the energy of the IR radiation matches with the energy difference of different vibrational energy levels. So, in this condition, vibrational transition is possible. Molecule may excite from the ground state vibrational level to higher state vibrational level. That means vibrational transitions are responsible for IR spectroscopy. Molecule as a whole, considered as ball and spring model. A simple covalent molecule is similar to ball and spring model. What is ball and spring model? In ball and spring model, balls of different masses are connected by a spring of different wave strength. It is similar to the molecule. A spring is similar to the covalent bond, and this covalent bond connects the atoms which are like the balls. When apply the energy to the spring, a spring can be stretched or compressed or bent. In the same way, since a spring and ball model is similar to the molecule, in which atoms are connected by a covalent bond which is like a spring. This shows the equilibrium bond length of the molecule. It is the normal state in which the covalent bond, like a spring, is always in the state of constant vibration. When we apply IR radiations are thermal radiations. These radiations absorbed by the bond, and covalent bond can be stretched, compressed or bent. This type of vibrations of covalent bond are known as molecular vibration. We can define molecular vibration by any change in shape of the molecule, like stretching of bonds, bending of bonds, or internal rotation around the single bonds. Whenever the interaction between the IR radiations and matters occurs, IR radiations in the form of energy absorbed by the molecule, and any of the changes in the molecule can be possible, whether it is stretching, bending or internal rotation. So this is known as molecular vibration. In organic molecules or in molecules, two types of molecular vibrations can be possible. First is the stretching vibration. Stretching vibration is the continuous change in the interatomic distance along the axis of bonds between the two atoms. That means on the same bond axis, the distance between the two atoms can be increases or decreases. Compression or stretching. This requires more energy. When requires more energy, appear at shorter wavelength or longer wave number. Stretching vibrations generally shows absorption at 4000 to 1400 centimeter inverse. To explain the stretching vibrations, here we are taking example of methylene group CH2, in which central atom is the carbon and two hydrogens are connected with the carbon. Two types of stretching vibrations are possible. It means on the same bond axis, two types of stretching vibrations can be possible. In case of CH2, both the hydrogens with respect to carbon can come closer to the carbon or can move far apart from the carbon. This is known as symmetric stretch. Symmetric, that means similar. As the name indicates, symmetric, movement will be symmetrical. Both the hydrogen atoms moves in the similar direction on the same bond axis with respect to central atom. Movement of atoms in the same direction is the symmetric stretch. Antisymmetric, one of the hydrogen atom come closer to the carbon and one is going apart from the carbon. That means movement is not symmetrical, not similar. This is known as antisymmetric stretch. One hydrogen is coming towards the hydrogen and one towards the carbon, and one hydrogen going apart from the carbon. So movement of the atoms in opposite direction is antisymmetric stretch. Second type of molecular vibrations are bending vibrations. Bending vibrations are also known as deformations. In bending vibrations, position of the atoms changes with respect to original bond axis. It also characterized by the change in bond angle between the two atoms. Bending vibrations requires less energy as compared to stretching vibrations. So they appear at higher wavelength or lower wave number. It shows absorption at 1300 to 666 centimeter inverse. Obviously, it is a practical concept. If we have a thick spring, it requires more energy for its compression and for its stretching, but we can easily bend it. So that's why bending vibration requires less energy. Again, to explain the vibrational deformation vibration, we are taking the example of methylene group. Bending or deformation vibrations are divided into two categories. First is in-plane deformation. In plane deformation, there is the change in bond angle on the same bond axis with respect to central atom. In-plane deformation can have of two types, scissoring and rocking. In scissoring vibrations, two atoms approaches each other. There is the change in bond angle. When the movement of the two atoms without disturbing or without changing the internuclear distance, their movement in the opposite direction or towards each other like a scissor. That's why they are known as scissoring vibration. In rocking vibration, there is no change in the internuclear distance. Both the atoms moves in the same direction. Movement of atoms in the same direction, in the same plane, without changing the internuclear distance. This is known as rocking. Both the vibrations are in plane deformation or in plane bending vibrations. Second type of bending vibrations are out of plane vibrations. In short, it is also known as OOP vibration. Double OP, OOP vibrations. Out of the plane vibrations are also categorized into two types, twisting and wagging. When two atoms with respect to central atom at one time they move upside of the plane and second time they move downside of the plane. Similar movement above and below the plane. This is known as wagging vibration. When one of the atom with respect to central atom move above the plane and other moves down the plane. This is known as twisting. Just like if we going to twist a band. So three types of vibrations in the any molecule is possible. Stretching can be symmetrical or antisymmetrical. In plane deformation, it can be scissoring or rocking. Out of plane deformation, it can be twisting and wagging. First four, symmetrical, antisymmetrical, scissoring and rocking. These are in plane vibrations. Twisting and wagging are out of the plane vibration. In stretching, symmetrical and antisymmetrical, only there is the change in the internuclear distance. In scissoring and rocking, there is the change in the bond angle, and other two are the out of the plane vibrations. To explain these vibrations, first we are taking the example of carbon dioxide molecule. Carbon dioxide is a linear molecule in which carbon is the central atom. Two oxygens are attached with the central atom carbon. Three types of vibrations are possible in symmetrical carbon dioxide molecule. First is the symmetrical vibration. In symmetrical vibration, both the oxygen atoms move in the same direction. When they are moving in the same direction, one carbon-oxygen bond length increases and one carbon-oxygen bond length decreases. Another is the antisymmetric vibration. Both the oxygen atom moves in the same direction, moves apart from the carbon or come closer to the carbon. This is antisymmetric vibration. And bending vibration, actually there are two bending vibration, but the energy required for both the bending vibrations, out of the plane bending vibrations, are similar. That's why they are considered as one bending vibrations or two degenerate vibrations. And in the last slide, it is shows different vibrational modes present in a molecule. Here we are taking the example of any alcohol. In alcohol, the carbon of alkyl group is attached with the OH group, carbon oxygen covalent bond and oxygen hydrogen covalent bond. The carbon oxygen covalent bond, in this bond, stretching may be possible, and carbon oxygen single bond shows absorption at 1200 to 1000 centimeter inverse. Similarly, oxygen hydrogen bond can be stretched. Symmetrical or antisymmetric stretching can be possible in OH bond, and it shows absorption at 3700 to 3000 centimeter inverse. If we discuss the bending vibration in carbon oxygen hydrogen bond, these vibrations can be in plane as well as out of the plane. Carbon oxygen hydrogen bending in plane vibration observed at 1500 to 1200 centimeter inverse, and carbon oxygen hydrogen bending out of plane vibration shows absorption at 650 to 250 centimeter inverse. It means in a molecule, number of vibrations depends on the number of bonds present in the molecule. Thanks a lot.